Hi everyone! We have introduced the EVPN VPWS over SRv6 BE scenario in the previous course. Today, let's take a look at the EVPN VPWS over SRv6 TE policy scenario. In this course, you can learn the similarities and differences between SRv6 BE and SRv6 TE policy scenarios. Let's still take an example of 5 devices to describe the detailed configuration and verification processes in this scenario. P1, the P and the P2 all reside on the public network. C1 and C2 are connected to customer networks. A bidirectional SRv6 TE policy needs to be established between P1 and P2 to carry EVPN VPWS. The configuration roadmap is as follows. First, enable is on P1, the P and the P2 to achieve basic route reachability. Second, configure an SRv6 TE policy between P1 and P2. Third, configure CE access on P1 and P2. In addition, establish a BGP EVPN peer relationship between P1 and P2 to transmit VPWS information between the PEs. For ease of understanding, we'll obtain packet headers from the two interfaces of P1 for packet parsing. In all SRv6 TE policy scenarios, is configuration, basic SRv6 configuration, and SRv6 TE policy configuration methods are practically the same. As such, they will not be described in detail. After configuring is and SRv6, let's check the SRv6 TE policy connectivity. If the connectivity is normal, we can then configure BGP. BGP EVPN configuration is mainly performed through the following 2 steps. First, configure an EVPL instance and CE access on each PE. Second, establish a BGP EVPN peer relationship between the PEs to transmit VPWS information. These configurations are similar to those in the SRv6 BE scenario. For details, you can see the introduction about the EVPN VPWS over SRv6 BE scenario. After the end.dx2 seed is configured, a local seed table is generated on the PE. According to the local seed table, we can see that the end.dx2 seed is bound to an EVPL instance. The EVPL instance is bound to an AC. As such, we can identify the corresponding AC connection based on the specified end.dx2 seed. Moving on, let's see how to establish a BGP EVPN peer relationship between the PEs. First, configure a BGP peer relationship between P1 and P2 and enable the peer relationship in the BGP EVPN address family. In this way, the BGP EVPN peer relationship is established. Then enter the BGP EVPN address family view and configure the device to advertise EVPN routes carrying SRv6 encapsulation attributes to its peer. Next, add the seed attribute to the BGP EVPN routes to be advertised in the EVPL instance. If no end.dx2 seed is manually configured for BGP EVPN, there will be a dynamically allocated one. Route recursion is required after route exchange. Route recursion is configured in an EVPL VPWS instance using the segment routing IPv6 traffic engineer best effort command. Note that we need to specify the traffic engineer keyword. In addition, we need to configure an EVPN source address using the EVPN source address 1.1.1.1 command. This configuration is very important. The configurations on P2 are similar. Next, let's see how to configure the route coloring function. To achieve this, we first need to define a route policy and specify the color attribute 0:101. The value 0, which is fixed, indicates the color flag. The color value is 101. Route recursion is allowed only when the color value of the route is the same as that of the SRv6 TE policy. Then let's apply the route policy to BGP routes to be received. The route policy can also be applied to the BGP routes to be advertised, but we need to configure the device to advertise extended community attributes in this case. Finally, we need to configure and apply a tunnel policy on the PEs to import the traffic on the CEs. The configuration mainly includes the following 2 steps. First, create a tunnel policy and specify the tunnel type to be selected and the number of the tunnels that can participate in load balancing. Second, apply the tunnel policy to the corresponding EVPN VPWS instance. After a BGP EVPN peer relationship is established, the devices exchange update messages to advertise EVPN VPWS routes. Let's take a look at the format of a BGP update message carrying EVPN VPWS route information. The message carries common path attributes, such as the origin, S-path, and extended communities attributes. Route target indicates the VPN target configured for the EVPN VPWS instance. Layer 2 attributes carry control word information, such as flags, which are typically used to determine the primary and backup PEs in, say, dual homing active-active or dual homing single-active scenarios. Because this example adopts single homing deployment, the PE must be the primary. In this example, the flags field is displayed as P flag, where P indicates that the PE is the primary. L2 MTU information is also carried to indicate the MTU of the connection between the specified PE and CE. In EVPN VPWS scenarios, the local L2 MTU must be the same as the remote L2 MTU. Otherwise, establishing a VPWS connection on the public network fails. After that, we can see the BGP prefix seed attribute. In this example, this attribute carries an end.dx2 seed, which is the same as the seed configured for the EVPL instance on P2. The attribute below BGP prefix seed carries network layer reachability information, referred to as an LRI. In this attribute, the main address family is the L2 VPN address family, and the sub-address family is the EVPN address family. We can see that the next hop of the route is the address of P2, and the route type is type 1 Ethernet AD. The route carries an RD and, most importantly, it carries the service ID of P2. After receiving the service ID, P1 matches it against the service ID configured for the local EVPL instance. If the two service IDs match each other, then a VPWS connection is established. In the EVPN routing table of P1, we can see type 1 Ethernet AD route information, which contains the ESI and service ID configured on P2. Because this example adopts single homing deployment, zeros are displayed for the ESI. The detailed route information contains attributes, the prefix seed carried by the route, and route type information. Next, let's verify the configuration. According to the EVPL instance information on P1, the EVPL instance is up and works in SRv6 mode. In addition, route recursion to SRv6 TE policy is performed. After a VPWS connection is established between P1 and P2, the CEs also send ARP broadcast requests to each other. In this way, the CEs learn information from each other and can ping each other successfully. This indicates that the configuration is successful. Note that the TTL value is always 255, meaning that it remains unchanged in the ping request from C1 to C2, and the ping reply from C2 to C1. This indicates that a virtual direct link has been established between C1 and C2. That's all about the implementation of EVPN VPWS over SRv6 TE policy in the control plane. Next, let's look at the packet forwarding process. Assume that we initiate a ping from C1 to C2 and obtain packet headers on this interface of P1. We can see that ICMP encapsulation is first performed on the original data, followed by IPv4 encapsulation, in which the source address is the address of C1 and the destination address is the address of C2. Then VLAN.1Q encapsulation is performed, and the encapsulated VLAN tag is 10. Finally, Layer 2 Ethernet encapsulation is performed. After P1 received a packet from this interface, It removes the VLAN tag and performs SRv6 encapsulation for the remaining packet data. Due to the binding between AC interfaces and EVPL instance, after P1 receives the packet over the corresponding AC connection, it can determine the associated EVPL instance, for which the recursion next hop is the peer and.dx2 seed. As such, in SRv6 encapsulation, the destination address is the and.x seed configured on the P, and an SRh containing SRv6 TE policy and and.dx2 seed information is carried. In EVPN VPWS scenarios, the public network transparently transmits Serie data. After receiving the ping request, Serie2 sends a reply to Serie1. Now let's look at the format of the packet that is sent by Serie2 and reaches P1 through P2. For this packet, the source address is the address of P2, and the destination address is the and.dx2 seed configured on P1. The highlighted data is still transparently transmitted. P1 then forwards the packet over the AC connection corresponding to the EVPL instance. According to the packet header information obtained from this interface, we can see that ICMP encapsulation is performed, and the packet is of the reply type. IPv4 encapsulation is also performed, in which the source address is the address of Serie2 and the destination address is the address of Serie1. When P1 sends the packet, it also performs VLAN.1Q encapsulation with the VLAN tag of 10. In this way, Serie1 can receive the ping reply packet. To conclude this course, let's summarize what we have learned. We first talked about ARP information transmission in the control plane. To achieve the transmission, we created EVPL instances on the two PEs, and most importantly, defined service IDs for the EVPL instances. A virtual private line connection is established as long as the local and remote service IDs match each other. Because the service IDs need to be exchanged, the EVPL instances need to be bound to EVPN VPWS instances, whose routes are stored in the EVPN routing table. In addition to establishing a virtual private line connection between P1 and P2, we established an AC connection between P1 and Serie1 and another one between P2 and Serie2. After all required connections are established on the public and private networks, Serie1 and Serie2 can exchange information through the connections. For example, they can send ARP requests to each other to request peer information. This is the implementation in the control plane. Moving on, let's look at the data forwarding process. The process of data forwarding from Serie1 to Serie2 is as follows. First, the original IPv4 packet is encapsulated with a VLAN tag and sent to P1 through the interface bound to the corresponding EVPL instance. Second, P1 finds the associated EVPL instance and next hop information according to the VLAN.1Q information in the packet, and encapsulates an SRh and and.dx2 seed into the packet. In the forwarding phase, according to the instruction bound to the first and.x seed, P1 decrements the SL value by 1, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the and.x seed. Third, the P searches the local seed table according to the outer destination address and finds a matching and.x seed. According to the instruction bound to the second and.x seed, the P decrements the SL value by 1, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the and.x seed. Fourth, P2 searches the local seed table according to the outer destination address and finds a matching and.dx2 seed. As instructed by the and.dx2 seed, P2 removes the IPv6 header, finds the matching EVPL instance according to the seed, and forwards the packet to the AC interface corresponding to the EVPL instance. That's all for this course on EVPN VPWS over SRv6 TE policy. Thank you for watching.